Okay, so Tony, are you ready?
Yes, I think so. So
yes.
Tell me when you want me to share my screen.
Yeah, you can share your screen. So, we had a little bit of trouble with the translator, but go ahead. So just share the screen and start your talk. Thank you.
Okay, so hello, can everybody hear me?
Yes, we can hear you.
Thank you. Thank you. Thank you very much. First of all, thank you very much for inviting me to speak in this arena. It's a great pleasure to be able to speak to people at the other side of the world. Yesterday, it's early morning here in Australia, so I'll try and not speak too fast. I know that I sometimes do that, so but I get excited about this topic. So I've actually prepared 2 talks, but we'll just see how we go in terms of the time. So the first talk is about patient-based real-time quality control. It's really an introduction to this topic. There's been a lot of work over the last few years, 5 years or so, about patient-based real-time QC, but in fact it's been around, the concept has been around since the 60s, really. So this is just another reinvigoration of an old concept. So what I'm going to talk about really initially is a bit about the history and what it's fundamentally, how it works. So that's patient-based real-time QC. Going to talk a little bit about then about the issues that are associated with it. One revolves around the IT requirements that you need to make it work. Then how do you optimize any application that you might get? How do you actually make patient-based real-time QC work with patient results? A little bit about the validation process. How can you validate that it's actually working optimally? And then how do you integrate it into everyday activities? So the first is a little bit about the concept of patient-based real-time QC. So what it's about is taking the results that you obtain on your patients and using them as the basis of your quality control. So you measure, say, sodium. Let's just pick a measurand like sodium. So we're measuring our sodiums, and we're going to use our patient sodiums or most of our patient sodium values as a form of quality control. I'm sure everybody who's out there who's run an analyzer at some stage, perhaps running sodiums or glucoses or hemoglobins, you often have a gut feeling that there's something wrong with the assay. For instance, with sodium, you normally expect most of your results for normal patients, or even for most patients in a hospital situation, you expect their sodiums to be sort of 139 to 142 millimoles per litre. If you start to see a whole lot of patients with results around 144 or 145, you think there's something gone wrong because you just don't normally see that. So that's what patient-based real-time QC is. It's taking most of your patient results, doing something with those results and using that as a form of QC, really to try and detect shifts in bias. So this is just a schematic, and I'll take you through the basic concept. So what we're going to do in this particular case of patient-based real-time QC, we're going to take a measurand, and again, for example, let's make it sodium. And we're going to take an average of previous results. So we're going to take maybe in this case 15 patient results, and we're going to take the last 15 patient results that we've analysed, 15 of them, and we're going to take the average. Okay, so last 15 results, average them out, and that's going to be our patient-based real-time QC average. On this graph, you can see a dotted line with a red series of red circles and a red dot, and some black points, the black crosses. The black crosses represent the real results, say sodium. The moving line going up through the middle represents the average, averaged out over the last 15 results. The box that you can see inside the axes, the box is the last 15 results, and the red dot represents the average of the last 15 dots. When the next patient sample comes through, we add the next patient sample in and take the last 15 results again, take a new average. So we've moved our average on, taking into account the newest sample, but therefore we drop off the last sample, the first sample that we used to obtain the previous 15 results. So the block keeps moving along. Each time we measure a new patient sample, we add that in, but we remove the 16th sample, if you like. So there's a constant block of 15 samples for which we're taking their average, and that average value is our patient-based moving average. That's the point that we use. And as you can understand, the point of this exercise is that if you've got patients who normally have results of sodium, say 139 to 142, if there's a shift in the bias because of something to do with the assay, calibration or reagents or something, and the bias moves, as you keep taking your averages, your average after 15 samples, the average will start to move up. And that way you can detect this shift. So that's all patient-based moving average is about. You just keep moving this point along, taking the new average, and that becomes your new point. So there's nothing new about this. The only thing that's happened recently is perhaps over the last 4 or 5 years, there's been a lot of work come out to look at really the theory behind how this works. That there was an IFCC working group formed in about 2017, and that group has published a whole series of papers about how do you actually do this? How do you make this patient-based real-time QC work? What's the theory behind it? How do you implement it? How do you validate it? What are the IT requirements? And then a few other papers really around reviewing all those processes. So that's what I'm going to talk about today, really, the work of that working group, these papers, and how they apply to what might happen in your laboratory. So as I said, there's nothing new about this concept. It's been around for a long, long time. And it's been around for a long, long time because it makes sense that there's some information that you can get from your patient values. Not all these patient values. So you know, in the case of sodium, in fact, you often get people with extremely high sodiums or low sodiums. So you can't take every sodium, but you can take most of your sodium values and use those. And I remember when I started in laboratories in the 70s, we used to do something like this. We used to take work out an average for all our patient results at the end of the week, and we just use that as a sort of a form of EQA, really. But it became sort of serious in 1965 when somebody, Hoffman, proposed charting the average of normals, patient normals. So they would remove all the abnormal patients and just take an average of just the normal values, and that would be used as a form of QC. It didn't really take off because it was seen to be too slow to act. It might be useful as a form of quality assurance, but it wasn't seen to be very useful as a form of quality control. Where it was successful was with in hematology. Bull in 1974 proposed a similar algorithm using patient results, particularly for the derived indices, the MCHC and the MCV, and his algorithm called Bull's algorithm, which was a moving average. It removed the outliers, but it basically was a weighted average. So it averaged the last 30 results of patients, and it took more notice of the most recent result compared with the oldest result. So it weighted them. So Bull's algorithm, as it's now called, soon became very, very popular, and it's now on nearly every analyzer that there is for some measure and. So the hematologists adopted this idea very, very early on. Why use patient-based real-time QC? Sometimes it's because other controls are just not available or impractical. And in fact, that's why the hematologists used Bull's algorithm. At the time in the 70s, there was no stable QC material available for hematology because they didn't know how to, have a form of QC that was suitable and was stable for any length of time. They've overcome that problem now, but in those days there was nothing. So that's why it was adopted. Patient-based real-time QC can detect errors that other forms of quality control cannot, and I'll talk a little bit about that later. The big thing, the big value of patient-based real-time QC is that in fact it's continuous. That's what the real-time comment means. So with patient-based real-time, every patient sample or nearly every patient sample is taken into account. So you take the next patient sample, and providing that next patient result is not grossly abnormal, you add that into the moving average or whatever it is you're going to use as your variable. You use that when every patient sample is used. On most analyzers in most laboratories these days, on the high volume clinical chemistry assays, you might put a QC material in, a QC standard in once a shift, once every 8 hours or maybe once a day. And in between those quality control samples, there may be hundreds of patient samples. So the one of the values of patient-based real-time QC is you get a lot more points where you can look at the quality of the assay. There's a lot more points, a lot more opportunities to detect an out of control situation because you're taking a lot more measurements that are used in your QC.
Tony,
Yes.
excuse me. The translator is now ready to go. We have some problems, so he is in now. So you know that you will be translated from now on, okay?
Okay, thank you. Thank you very much. So I understand I'm now being translated. So thank you to the translator. And I hope that people haven't missed out on too much of the talk. So I'm really now talking about what are the advantages of patient-based real-time quality control. And I've mentioned that already that the advantages are that sometimes conventional quality or any form of quality control material isn't available, that in fact patient-based real-time QC can detect errors that conventional quality control cannot detect. Patient-based real-time QC uses a lot more points, control points. So rather than putting a quality control sample, every 800 samples or every 8 hours or once a day, you get a lot more measurements. All your patient measurements, or nearly all your patient measurements, can be used in determining the quality control parameter. There's little cost once you've set the system up. There's little cost because you're not using external quality control material, and the sample is certainly commutable. I think we're all aware now that there are problems with artificial QC material in that the changes that you might see in an assay as detected by the synthetic QC material might not be evident in the patient samples, and that's because the QC material is not commutable. Well, patient-based real-time uses patient samples, so it is commutable. It's useful. Patient-based real-time QC is useful to detect lot-to-lot variation. In that you can look at your moving average over years and see if it's actually changing, if the moving average value is changing. So you can see over a long period of time if there's been any shift in your average patient value, which reflects, if it is, either long-term changes in calibration or long-term changes in the reagents. And you can pick up pre-analytical factors. And the way that you can pick up pre-analytical factors is, that if there are problems with phlebotomy, if there's a collection room or a collector who may not be collecting samples as well as they should, so that there's more hemolysis in those samples because of the traumatic collection. And we often see that in ward collections, in ICW, or in some collections where they use a needle and syringe. Often yourself that when you see those samples coming from one place, there's increased LD, increased potassium, or sometimes there could be a problem with the transport of samples, either through a vacuum tube system or maybe by road transport. And you can also see the same thing, that the samples are slightly more hemolyzed, the glucose is a little bit lower or whatever. So you can pick up those sorts of variations in patient results too, if you collect enough information about the patient sample. So patient-based real-time QC can pick up some pre-analytical errors. So I'll just go through now, based on a lot of those papers, some more key things about patient-based real-time QC. So what you need to understand if you're going to implement patient-based real-time QC, you need to understand fundamentally three things. You need to understand, for the test of interest, be it sodium or whatever, you need to understand the biological variation of that test, because clearly if the test varies, if there's a seasonal variation, or there's a variation because of sex or age, that's going to have an impact on the average of your patient values. So for instance, with vitamin D, you know there's a seasonal variation in many countries, depending whether it's sunlight or not so much sunlight. So the vitamin D levels will change during the year. You need to take that into account. You need to understand the analytical characteristics of the assay. You need to know, how good is the CV going to be for the assay. You need to understand your population, your patient population. And as I said, you need to know if the thing that you're measuring, the analyte that you're measuring, if there's a difference in males and females, or a difference in children and adults or elderly people, because you will have to identify that in your populations. You may have to have a population for males and a population for females, for example. You need to understand also in some situations, in hospital situations, there may be different patient populations in your lab samples during the day. You may, in a hospital situation, get more inpatients in the morning and more outpatients in the afternoon. You may get a lot more inpatients over the weekend than you do during the week. You may get more abnormal samples in the morning, because they may come from the acute care wards like intensive care or cardiac care. They often come down in the morning after the first sort of bleed for the day. So in the morning, you may get a different sort of average sodium than you might in the middle of the day, where it's more inpatients, than you may in the afternoon, where it may be outpatients. So you need to understand that. You need to understand that on Tuesdays, maybe you might get a diabetic clinic, so the glucose levels might change. You need to understand that maybe one day in the week, you might get your renal patients. So you need to be aware of the patient population in your hospital day by day. And you need to understand what capability your laboratory information system has. If you're going to do a lot of these calculations, and really, when you think about what I've suggested, each time you do a new measurement on a patient sample, you're going to include that newest result. If it meets certain criteria, you're going to include that result in your moving average. So you're going to reject or remove the oldest in the block of 15 or whatever it is, add the new one in, do a new calculation, there's your new point. If you've got 20 measurands on an analyzer, every sample is going to have 20 new points. If you've got 5 analyzers, every analyzer is going to be analyzing 20 measurands on every sample. That's a lot of data. So your IT system has to be able to do all these calculations. And that's one of the reasons why patient-based real-time QC is now more of an option than it has been in the past. There is greater IT computing power available to do these calculations. That's another reason why it's now more possible to do this sort of QC. So I've talked about a couple of things, but I'll now define better the sorts of parameters you need when you're considering applying an algorithm that can be useful for patient-based real-time QC. So I've said that you might, in the case of sodium, you might want to exclude very, very high patient values. So we call that truncation. So for sodium, you might want to remove all those patients who have got sodiums above 155 and below, say, 125. So you want to truncate out those extreme values. Remember, when the first attempt to do patient-based real-time QC was in fact the average of normals in the 60s. And in fact, all they took were those patients in the reference interval. That actually loses a lot of information. So we don't do that anymore, but we certainly, we remove the highest extreme values. So you can imagine with an enzyme like ALT, you might have some patients with ALTs of hundreds. You don't want them in the calculation because that one patient will affect the average. So we truncate, we remove the most extreme values. We may want to exclude certain patients, not just their values, but the actual patient. So as I said, you may have in your hospital population, you may have diabetic clinics and renal clinics. You may have patients who have just had transplants with very high, bilirubins or very high creatinines. You may have pediatrics, so very young babies. So you don't want those patient results to impact on the moving average. So based on a ward or a patient even, you may exclude particular patients. So not just their values, but knowing that this group of patients or this particular patient will always have abnormal results, you may want to exclude them. You want to take, the next thing you want to do is if you're working on an average, you're going to average a certain number of patient samples. So the number of patient samples that you average is called the block size. So you want a block size. And the block sizes vary. They can be quite small, 5 or 7, or they can be 70 or 80. So, but that's the number of patients that you take to work out your average. In fact, what you can do is you can have different algorithms with different block sizes. So for sodium, for instance, you might want to take a block size of 10, so the last 10 patient sodiums, and take that as an average. And that will detect if there's a sudden change in the average. So that's very useful for detecting error that occurs rapidly. For sodium, though, you might also want to take a block size of 70 or 80. And that takes the average over a much larger number of patients. And that's useful if you want to look back over a long period of time and see, in fact, if there's been any change in your sodium mean over a long period of time. So different block sizes can tell you different things. One block size tells you whether or not, the small one can tell you whether or not you're going out of control now. The larger block size will tell you if there's any lot-to-lot or calibration changes. So you can use it to look back over a long period of time and see if you've got gradual changes over a long period of time. And then, of course, another key parameter is what algorithm are you actually going to use? I've kept on talking about means, taking a mean of the last 10 or 20 or whatever it was, but you can use lots of different algorithms. You can use a median, particularly if the patient results are not normally distributed. If they're distributed in a way that's where there's a skew in the distribution, for like some enzymes, for instance, you might want to use a median rather than a mean, because we all know that medians are less affected by the distribution. You might want to do something where you weight the most recent result more heavily than an older result, like Bull's algorithm. So what you might do is you still take your median or your mean, but you weight the most recent results more heavily than an older result, so they have more impact. So that's called an exponential weight. But in fact, there are many other algorithms that you can use. And I'll give another idea shortly about the range of different algorithms that you can use. So means and medians and exponential medians are some, but if you think a bit more broadly, there's lots of other information that patient results can tell us that you can use in this form of QC. So now this table just compares patient-based real-time QC with conventional QC or statistical QC, and there are lots of different things that are different, but really the main things are the frequency. I say with patient-based real-time QC, you're basically measuring and adding to your algorithm with nearly every patient result, rather than waiting for the next synthetic quality control sample, which, as I say, might happen at the end of the day or at the end of the shift or whatever. So there's a lot more data. It's commutable with patient-based real-time QC by definition, because it's patient samples. It's can detect some pre-analytical phase problems. As I said, really, if you collect the information about the sample and where it's collected, you can detect things like poor collection process or transport problems. One of the problems with patient-based real-time QC, though, is that it's an average or a median for all the sodiums, for example. So you only have one level, and effectively, it's the middle of your reference interval for your population. So whereas with statistical QC, you know that you normally run two samples, a normal and an abnormal in conventional QC for clinical chemistry, routine clinical chemistry, and maybe three samples for assays where you're also interested in low values as well as high values. So in many immunoassays, you may have a normal QC, a high QC, and a low QC. You don't have that in patient-based real-time QC. And if you're wondering what it looks like in terms of a plot, it looks just like this. So this is an example of a patient-based real-time QC Levy-Jennings chart, effectively, for albumin. And you can see it looks just like everything you're used to. There are some control limits on the side. There's a pink area, which describes when you're out of control, and there's a green area when you're in control. And the 0 point represents the long-term average of the samples. So this is results for, as I say, for albumin over a period of time, every 7 days. And there's a couple of things that are interesting about this. You can see there's a sort of periodicity about it. You know, there's a very strong pattern that you can see, and that reflects to some extent the patients that are seen on different days. So you get a lower value when there's a lot of inpatients for albumin, because inpatients have lower albumins. But you can also see during the day there's sort of sawtoothing as well. So there's information there about the assay or information about your patient population. So you need to be aware of that there's information about all sorts of things in this data. It's not just about the analytical process, it's also about your patients. And this was a paper put out by Fleming and Kadiev. And what was interesting about this paper was that there are lots of different things, different algorithms that you can use. I've mentioned means, medians, weighted means, but in fact they used logs of sample of results, square roots of results, and medians as well as means of those things. In fact, this was quite an old paper now. We now, rather than go through these sort of options, we now use a Box-Cox transformation. So we optimize what the algorithm should actually measure. But there's other things you can use as well. So this is a couple of papers that came out a little while ago. So when you think about it, if you're measuring the mean of a population, you know that there's also going to be a standard deviation associated with that population. And one of the things that we don't measure well with conventional QC is changes in the SD of the assay. An increase in the imprecision of the assay is very hard to measure. Bias is relatively easy to measure if there's a change in bias because of calibration. But if the assay increases its analytical variation, its imprecision, it's very hard to measure that. But using patient-based real-time QC, you measure an SD, or you can measure an SD, so you can see if there's a change in the SD, which will represent an increase in precision of the assay. The other thing that you can measure are the number of outliers, and that is the number of patients that are outside particular limits. Those limits may be the reference range. So you might want to measure any samples that are above the reference interval or below the reference interval, because that's telling you something. And when you think about it, if you have a change in bias, what you will see, therefore, is more patients being, if it's a positive change in bias, so the bias moves up, you're going to have more patients flagged as abnormally high and fewer patients flagged as abnormally low. So by measuring the number of patients who are above or below the reference interval, that can give you information about bias. It can give you other sorts of information as well too. This paper was, the top paper, was written about PSA. And I'll tell you the story because, again, it shows how useful the concept is. This is a true situation. There was an assay, a PSA assay, that was being used in one hospital to detect, after post prostatectomy, to detect recurrence of prostate cancer or failure to remove the entire tumour. So post prostatectomy, you would expect the PSA should be 0. And if the PSA is there, it means that there's either secondaries or that the surgeon hasn't removed everything that the whole tumour. So, but the surgeons, the urologists, look at very, very low levels of PSA. So basically, if there is detectable PSA there, at the very limit of detection in the assay, a surgeon may well think there's a problem and start to monitor that patient. So in this particular hospital situation, the surgeon used to be aware that, in normal post-prostatectomy in most patients, the recurrence rate after that was something like about 20%. So of all the patients that went through the surgery, after surgery, only about 20% of them had any residual PSA there, or after 6 months would have detectable PSA. He started to notice that, in fact, his patients, the PSAs on his patients, started to, there were a lot more positive results, a lot more patients post-prostatectomy that had detectable PSA. And in fact, it got up to about 70% of his patients after the procedure, after surgery, there was detectable PSA. And he queried the result. He said, it doesn't, there's something wrong. It's so different to what I'm used to that I think there must be a problem with your assay. And the laboratory, didn't really react. And partly why the laboratory didn't react was that their PSA assay, their standard PSA assay, was really optimized to detect elevated PSA. And certainly their quality control samples were at the sort of the top of the reference interval, and then at a much higher level. It's sort of a level of 4 and a level of sort of 10 and that. But these changes in PSA that the urologist was after post-prostatectomy were levels around about 0.08, at the very, very limit of detection of the assay. So the laboratory's QC could not detect that there was a problem with their assay at the low end, at the limit of detection. And yet the surgeon knew that there was a problem because he never saw these positives before. So you can use that same concept to detect a problem with your assay. So that's called the number of patient positive results, in this case post-prostatectomy using PSA. So you know what the normal number of patients should be who have a positive PSA post-prostatectomy, and in this particular case it was 20%. So as soon as you start to get more than 20% of your patients positive with this PSA, this particular PSA, there's probably a problem with your assay. Okay, so what it's measuring is the number of patients who are positive compared with the historical number that were positive. And you can do that for all sorts of things. You can do that for semi-quantitative assays like Hep B positive assays, where you just measure a positive or a negative. You can use it for those situations too. So the concept can be used in lots of different situations. And this was a paper that was published a little while ago, last year, and it uses the same concept, the number of positive patients for troponin T. So even though that's a quantitative assay, you can use the same concept. So they found that the moving average, the moving number of patient results, abnormal results, was in fact it detected was better than their current QC system, and it outperformed both the conventional QC and in fact moving average as well, because normally with troponins, depending on the hospital situation, you have a lot of negative results and only a few positives. And you're looking at limits at the very, at very low levels of sensitivity. So it can be used for all sorts of things. So this is a nice graph from Hoob, and it just tells you when should you consider using patient-based real-time QC. One, if there's unstable or no stable material available, and that still occurs with some assays. There is just no QC available. If there's instability because of pre-analytical issues, some assays we know that the results are not stable. The QC material, is not stable, maybe bicarb. If in fact the assay is prone to have sudden shifts and they're hard to detect with conventional QC, and they're hard to detect with conventional QC because you don't run a lot of conventional QC. Now, things like albumin, like calcium, the QC is unstable, can change, and to keep it truly in control, you need to run a lot of QC material. If there's a commutability issue, where the QC sample might not be commutable, and in fact, it's been shown that conventional QC might not follow a Gaussian distribution. Or if you want to, if there's been problems with lot-to-lot variation, where you really want to look at what's happening with my patients over a long period of time, you should consider patient-based QC. So that's the other thing about patient-based real-time QC. If you're monitoring using patient-based real-time QC says that it's increased, say for sodium, it's increased by 2 millimoles, that means that your patient's results have increased by 2 millimoles. That doesn't always occur with conventional QC. Just because the conventional QC value changes by 2, that doesn't mean that your patient values have changed by 2. With this, it does, because there's no commutability issues. And the last thing that's where you should consider patient-based real-time QC is if your sigma, your sigma value for your assay is less than 4. And in all reality, nearly every assay that we run, the sigma is less than 4. It's very, very unusual for any of our assays to have a sigma greater than 4. That's just the reality. But you certainly need at least 10 results per day. To make patient-based real-time QC, you've got to take an average or a median or something like that, where you do something with a series of patient results. If you've only got 5 samples, taking 5 is not going to work. You're better off just putting a conventional QC at the beginning and the end of the run. Okay, so there are limitations. So I'll talk about the IT requirements. So the data that this is in a paper. So these are all in papers. So I'm not telling you anything that you can't find. So the information that you need are sort of the parameters from the assay, when the assay was done, the sample identification, to be able to do that fine pre-analytical error detection. You need information about the patient, because you might want to exclude them if they're from a particular ward or it's a particular patient. You need the sex in case it's a hormone where there's a sex difference. You need the laboratory equipment, the sample type, the collection information, again, to detect, if there's a problem with the way it's been collected or transported, and you can see that other sort of information. All this information obviously comes from the laboratory information system or the hospital information system, but you start to integrate all of that into your QC. The essential features of the middleware needs to be able to capture, store, extract, present the data, etc. So you need a good onboard or middleware system to be able to do this. And again, in this paper, we also gave what would be even more useful to have, and there's some more tools that would be useful to have. And again, this is from a paper from Huub van Rossum, which also goes through the same sort of issues about what do you need, and to set up a patient-based real-time QC system, and things like being able to reset the average or the mean after there's been alarm. You need to be able to reset that. You need to be able to get alarming so that if something goes wrong, somebody is detected, and you need to be able to have suitable control limits that are in the software, and to be able to calculate with useful frequency. These are useful if you're talking to your vendor. I'll mention this later, but lots of vendors have got some sort of middleware. The Roches and the Abbotts and the Beckmans have got some sort of middleware, but at this stage, in many cases, it's not as good as it should be, because in many cases it doesn't contain lots of these options. And this is, in fact, this is fairly old. This comes from an old paper now, and some of this has changed. But this shows you that for different providers, they do in fact have some options available. So the suppliers have been thinking about patient-based real-time QC for a long time, and many of them have got some sort of algorithms in there. But in terms of the best middleware that's available, currently that's provided by Data Innovations, a software provider. So the way that you optimize this, that with conventional QC, we all follow the power function curves, and we use that to optimize, the frequency and what rules we should use. With patient-based real-time QC, the sorts of things that you optimize are the truncation limits, and where you cut off your high and low values, and this just shows you that for creatinine, based on if you cut off at 150, you can see the effect of different batch sizes. So these batch sizes represent the number of samples you're going to use to determine your average, and if you use a different batch size, you get more detection success with different truncation limits. So you need to play with that combination of the number of samples that you use to work your moving average out, and where you for creatinine, where you cut or truncate your highest and lowest values, highest values for creatinine. There's a paper that was written in Clinical Chemistry 2 years ago, I think it was, by the group, really, which shows how to optimize patient-based real-time QC using simulation. And this paper also has the advantage that it provides a link to the software, which is freely available. So you can use your data using this software and put your data or your population data in there and play with it, and it will allow you to optimize and set the best algorithm, the best truncation limits, the best block size, and so it does the hard work for you. You really need to do this using simulation, and you must simulate using your patient data, because as I've said, depending on your inpatients, outpatients, age of patients, season, you will get, the parameters will be different. So you need to simulate using your patient data, and you get nice curves like this, which demonstrates, for a variety of parameters, how you actually optimize using your patient data. So it's a very good paper if you're interested, and the software is free and quite easy to follow. This is again an example from the from that paper, a printout of the data using some data that's also been provided, and it just shows you, which which algorithm is optimal depending on the block size and the truncation change. So it's a very, very useful paper. So validate. So then, once you've got the optimal algorithm, how do you, in fact, prove to somebody, mainly yourself, but also to any external agency, that in fact I've validated my data? And this is some recommendations for how you do that. But I always think about the question. The current QC that you use, Westgard rules, they haven't been validated. But we need to ensure that anything that we put in is at least as good as the current system that you've got. So this verification paper really describes how to do that, and how you actually go through and prove that in fact you've got a valid verified process. And it describes here, using a table like this, what information you need to have in terms of demonstrating to any auditor. This is I've proven by using this sort of process that in fact what I've got now is at least as good as what I've got before. This is an example of how you can validate your data. So what this shows is a patient-based real-time algorithm flowchart. If you look to the left, that represents in control. You can see that the little blue dots, which represents the moving average data, it's between the red lines, so it's in control. What you do in a simulation process, so that represents your patient values when you're at a stable part of your stable assay. You add to that data in a simulated way, you add a bias. So you add, if it's sodium, you might add +2 or +3 sodium to simulate that there's been a shift in the assay, and you can see the effect as the blue line, the blue points, which represent the moving average points, the moving averages, go out of control. So in the top graph, there's been a positive bias added. In the bottom graph, there's been a negative bias added. So you can see by doing this process in simulation how long it takes, and that is how many patient samples does it take, using the algorithm, using the control limits, using the truncation limits. How long does it take before you can detect that you're out of control for both a positive and a negative? And a positive and a negative are given because sometimes the control rules are more effective at detecting positive error than negative error. So you need to detect both. And what you can do then is you can change the algorithm or change the control limits or change the block size and keep doing that over and over again, or getting your simulator to do that to optimize that data. That previous paper that I mentioned, in the clinical chemistry paper with the software available, that does all this for you, but this shows you what you need to do to simulate that you can actually detect an error. And then the question of integration. So how do you integrate patient-based real-time QC into your routine laboratory process? So you need to have recommendations for the management of your settings. Who's going to be able to change these settings? What happens when there's an alarm? If there's a flag, what are you actually going to do? And again, this is from another one of our papers. It suggests you should stop reporting, move samples to an alternate instrument, determine whether or not when the error occurred, and how you should detect the size of the error and what you should do to sort of troubleshoot the problem. And then how do you go through the alarm workup? So there's some practical suggestions here as to what you should do if you've got an alarm with patient-based real-time QC. Most of this is sort of common sense, but it's walking you through every process, just so there can be no questions about the validity of this process. This is from another a paper of Van Rossen, which also goes through the same issues, and it suggests what you should do in terms of optimizing and validating your patient-based real-time QC. So there are a number of options out there for you. And from that same paper, this really goes through for a particular laboratory, a number of measurands, and sort of block sizes, why they used patient-based real-time QC or moving average. Sometimes it was because there was instability in the case of bicarb. Sometimes it's because there was a critical error with creatinine or potassium or sodium, or sometimes the signal was less than 4, as there was with albumin and hemoglobin, etc. So you can also see here that they use the same processes for some hematological parameters, not just the ones that are usually used for Bull's algorithm. So labs are really using this. The other thing about integrating patient-based real-time QC is how do you integrate patient-based real-time QC and conventional QC? You can run them in parallel, so run both patient-based real-time QC with routine QC. That's what most people are doing now, because we still need to get confidence that the patient-based real-time QC will tell us stuff and be as good as a conventional QC. Eventually people move towards using patient-based real-time QC as the main form of QC, and then they use conventional QC if patient-based real-time QC goes out of control. So when it goes out of control, they'll use some conventional QC just to validate that it's out of control, and then they'll troubleshoot using conventional QC. This is a very common model, and in the US, the laboratory that's using patient-based real-time QC, and as far as I'm aware, has been using it for the greatest length of time, is LabCorp. So LabCorp use it in their clinical chemistry labs, and this is the form of QC that they use, a combination of patient-based real-time and conventional QC. What that lab's been able to do, as reported by Fleming and Katiev, is they've been able to reduce the volume of conventional QC that they use by 80%. And they've also validated that, in fact, they've got much greater detection of error capability. And the last option, which will be where I think eventually laboratories will end up, is that not to use conventional QC at all, where you just do everything based on patient-based real-time QC. And if patient-based real-time QC flags that you're out of control, what you will then do is go back to previous patients earlier in the day, or patients that might be stored, and use those samples to troubleshoot and to see where was the problem and have I solved the problem. So you use previous samples when you were in control as your troubleshooting process, rather than synthetic samples, synthetic QC. And the problem with conventional synthetic quality control material is it might be non-commutable. So you might be troubleshooting a problem that is in the material and not in the assay. So that's why eventually I believe that we'll end up with option 3 for many assays. People often ask, well, will this pass regulation? Will this pass accreditation? And in most jurisdictions, accreditation requires that you do some form of QC, but it doesn't dictate what the QC should be. And I like to include this graph, this photo, because it describes what's going on in your assays currently. You know, if you're using just conventional QC, just a QC sample every 100 or 200 or samples, or every 8 hours, you don't know what's going on most of the time. You only know when you run your QC at the end of the day or after 8 hours that something's gone wrong. And if something's gone wrong after 8 hours or 200 samples, what are you going to do? Are you going to rerun all those samples? Because most of them you would have reported the results. So you're going to rerun all those samples and then notify clinicians that these results are wrong. Is that what you're going to do? Is that what people actually do? Our analyzers are very, very stable. So we don't often have this problem. But when we do have this problem, it's a problem. And when you think about it, if you only run conventional QC at the end of the day, at the end of the shift, it's quite likely that the person who has to make the decision about rerunning samples, about notifying clinicians that there's a problem with the results that have gone out, can be quite a junior person. It can be, in the early evening or late evening, depending how your laboratory works. It's a risky process. So other applications. So in terms of moving average algorithms. People have published on using the algorithm with conventional QC samples. So if you use conventional QC samples, you run your, rather than using Westgard rules, if you actually just use an average of normals, a moving average data plot, you can in fact, it can be just as useful as Westgard rules. In fact, more useful. And the other thing that this concept lends itself to is external QA. So in fact, there's an external QA process available now, run out of Noklis in Norway, where you send every day or every week or every month, depending on your data size, you send to them your moving average value for each parameter that you measure. And so you're compared, your lab against yourself, against your method, against all methods for a particular measure and for your moving average. So, and that's some data. And you can see if in fact your moving average is doing the same thing as everybody else using your method or all methods. And it's certainly detected problems where there's been a calibration change in a particular reagent lot for a particular manufacturer. Or the other thing you can do is and again, this is also provided, this is an EQA provided by Noklis, the Norwegians. You can use, as I mentioned earlier, you can use the percentage of your patients that are above the reference interval or below the reference interval. And again, every day or week or month, you send that data through and you can see how your assays are performing in relation to the number of patients that you're declaring as being abnormal. And that's a very useful EQA and QC parameter as well, as I said. So those things are actually being used as EQA. And I actually believe this is going to be the future of EQA. But this involves collecting big data. And that's where labs need to be. This just shows that, in fact, this is again a paper from Hoob, Van Rossum, and it just shows you that, in fact, laboratories are using patient-based real-time QC. And laboratories such as these laboratories, the Cancer Centre in the Netherlands. So these are laboratories where you would think that there's a lot of abnormal results. It's not going to work, but in fact it works. There are limitations though, and not every measurand is amenable to monitoring by this. So you need different strategies, and some of those different strategies may be that you measure, as I said, the percentage abnormals above or below the reference interval, or the percentage that are around or above a sort of a cutoff, as is used with the PSA. So that's what I've mentioned. And if you've only got very small run sizes, you're not going to have enough samples to be able to get useful data. And its greatest value is in results that are where you don't have a large number of abnormal results, such as in some tumor markers where there's a significant degree of skewness. So this, in terms of the future, many laboratories do not use an evidence-based strategy, and that's been shown. There was a paper that came out in the American Journal of Clinical Pathology in 2018, where this was a conclusion of a survey of 21 very good laboratories in the US, that in fact that most of those laboratories, and I know most laboratories in Australia, and I know most laboratories in the UK, despite all those Westgard rules, most people just use the 2S rule. If it's outside 2S, they'll run the sample again, the quality sample again, and if that one fails, they'll say that the assay's failed. But that's not a well validated process, and it's not an efficient process. So most laboratories don't use an evidence-based strategy for QC. But the other thing that I think is going to have to happen is that, as I mentioned earlier, there are thousands of results that are going to be coming your way in a laboratory when you start to adopt patient-based real-time QC. And that's because every patient sample is going to be, or nearly every patient sample is going to be used as part of the quality control process. So every one of those is going to add to a new moving average for every measure and that the patient sample is measured for every sample. So there's going to be thousands of results. So humans can't cope that amount of data, we're going to have better software to do the QC for us. So that's the other big change I see that's going to happen. We're going to move away from somebody sitting there in front of a terminal and watching QC Levy-Jennings plots to it all being done by automatically. So just in summary, I think QC has become in many laboratories poorly understood and practiced, and it relies on compliance rather than based on risk. Patient-based real-time QC is based on patient risk. You measure it all the time, and you're measuring patient samples, so you're measuring changes in patient results. It is much better detection than conventional QC. It can be too sensitive sometimes, and there's virtually no cost. There's a lot more to learn about analytical error by challenging conventional dogma. So we need to think about what we're doing. QC is one of the most important things we do in laboratories, but we need to be open to change in regard to managing risk. And it's about time. This is an editorial from Curtis Parvin written a few years ago now, but it's about time we started to think about the way we do QC. And thank you.
Thank you very much, Tony. It was such a very useful and important conference. Thank you very, very much, especially because you are over there very early in the morning, and I hope that you can have a cup of coffee after this.
It's 2:20 a.m. currently, so but it's tomorrow, so and tomorrow's a lovely day, I can tell you. So
okay, good. Happy to hear that. So yeah, no, we have now some time for questions and answers, and I will appreciate to have, let me see, the audience, that I bet that there will be several questions. Let's see if we can read those questions here. Hold on a second. Okay, everybody's saying that it was an excellent conference. Thank you very, very much. And well, there is one question here. Wait a second. When you are talking about, let me see, because it's moving up, so I'm losing the question. When you are talking about quality control, commercial quality control, are you talking about animal-based quality control, or it's a liquid-based quality control? Can you give an example?
So this is the sort of the I don't want to name something, but it's usually that it can be it's the samples that we use currently to monitor our QC. So they're often lyophilized samples that you add something to, or they can be liquid samples as well. They might be human-based. They don't need to be animal-based. They can be human-based as well. But that material, the way that it's produced, and it's the way we produce EQA as well, I hate to say it, but they pool samples. But to get the concentrations that you need, particularly for the abnormal samples, they normally strip out lots of measurands and they add new measurands in. And some of the measurands that they will add to get the high values will be synthetic. They might be, to get, high levels of bilirubin or ALT, or they'll add something. Often, they might come, that might be based on animal sources, or it might be synthetic material, synthetic proteins. So what happens is the sample ends up not being a patient sample, but it contains lots of things. Tumor markers, they might not be human-based. They might be, grown in a laboratory. So that material doesn't behave the way that human samples behave. So just going through the lyophilization process, they'll often add antibiotics, for obvious reasons, or they'll do other processing with the material. So again, that changes the matrix. And for small things like small molecules like sodium and urea, it probably doesn't make much of a difference. So they probably are commutable. But lots of the larger molecules, particularly in immunoassay, that the synthetic material may not have carbohydrates, might not have the same targets, antibody targets that real human material does. So that's the problem. It doesn't behave the same way that patient samples do. And you know yourself, with the best will in the world, you make up a QC material and you put it on the analyzer, and sometimes there's evaporation, or somebody mightn't make it up correctly. They might add enough diluent, or it might go off. It might be left out the bench for a little while, and the bilirubin. So all those things mean that the sample, the QC sample, doesn't reflect patient results, and it may in fact deteriorate over time for one reason or another, or it might not be made up properly because of one reason or another. Or some batches of QC material, the glucose deteriorates over time. So all those reasons mean that a lot of the problems that we have with QC material, when we use synthetic QC material, often relate to the material itself rather than the assay.
Okay, that's very good. Thank you for your answer. There is another question here. Let me see, going up because okay, hold on. Okay, what is the there are a couple of questions more, but they're moving here. What will be the difference between conventional quality control and the quality based on real-time patient samples? The essence of the difference.
So can I have, I missed it. So patient-based real-time QC, and what was the first option? The difference between that and conventional QC? Was that the question? Sorry.
Yeah, the question is between real-time patient blood real-time samples and conventional quality control.
Well, I guess the main differences are that with patient-based real-time QC, you're effectively using nearly every patient sample as is part of the process. So if you're measuring sodiums, every patient sample, unless it's 180 or 120, the sodium value of that patient will be taken into the calculation. So if all of a sudden you get a shift in your QC, if you get a shift in your assay because you recalibrated or something, and your sodiums move up by 2 or 3, you will detect those fairly quickly because all your patient samples will be higher. So if you use conventional QC, you might not run another quality control sample for 8 hours. So you're not going to pick up this shift until 8 hours later, depending when the shift occurred in relation to the QC. So that's one thing. You're monitoring all the time rather than just when you have the set QC samples. It represents your patient population. So it may well be for your hospital, your patient sodium value is 138. And that's just because you've got a mixture of inpatients and outpatients. For another hospital, it might be 142 because they have a different climate. Maybe there's more. I don't know. So it's very specific to your hospital. The other thing is that it's commutable. Because you don't have those issues that I've said, and the other thing is that you don't pay anything. Basically, you're not paying for those external QC samples. It's all with your patient samples. You have to have the software on board. That's what's missing now. It's coming. The manufacturers are seeing the value of this, and they see it as useful for their analyzers to be able to sell to you to say, buy our analyzer. We can do all these calculations, and you don't have to buy external QC. That's the selling point for them. But really, it's the same as, if there's any hematology people out there, it's the same as Bull's algorithm. That's a form of it that we've used for 40 years or 50 years or something. So it's the same. The machine just does the calculations for the MCHC or the MCV, whatever they are. I'm not a hematologist, and they're just there, so they're there based on the normal patients. So, you don't need QC because it's all done by the instrument.
Okay, one more. It says, what about biological variability requirements. Do they apply to this type of patient-based real-time quality control?
It certainly does, because, as I said, when you think about it, let's look at vitamin D. Vitamin D, the average vitamin D in the population, depending where you are and depending how exposed you are, to sun, your vitamin D levels for the population will go up and down between summer and winter. So yes, you will have a lower mean of vitamin D in winter than you will in summer, probably. With males and females, obviously different hormone levels they'll give you different levels for males and females. So biological, that sort of biological variation is there all the time. And what you're really doing when you're looking at your patient-based moving QC it's effectively a reference interval. When you think about it, it's the average or median of your sodiums or glucoses or whatever for your population. It's your patient population. So it's the mean of your patient population. You could use as your limits, the top and bottom of the reference interval, but in fact, in practice, we don't do that, because sometimes that can be too slow. That change can be too slow to detect a significant problem. So sometimes you do something better than that to detect when you're out of control. But you are effectively using the reference interval for your population when you're using patient-based real-time QC. It's very much related to the whole concept of biological variation. You're using the biological variation, the mean or median of your patient population. When it changes, if your population hasn't changed, your assay must have. So that's the basis for it.
Okay, and one more, and that will be it, because we have several others, but they are a little bit more long, and you will probably have to take more time to speak it. And I think we must be cautious with you.
If you send me the questions, I'll answer them and send them back. Yep, yeah, I'll do that. That's no problem.
We'll do that. But the very last one, what will be the minimum number of samples that you need to do this analysis?
It varies on the measure and on the analyte. So it varies very much on the measure and your population. If you've got a population where they're all normal, you might be in a community practice where they're basically all well people, you don't need as many to detect a change. If you're in a hospital population where you might have a greater variation of ALTs or something or other, it's going to be harder to detect a shift because you've got a much wider range of sort of normality. But the numbers can vary from, I've seen numbers for sodium as low as 10, so 10 patients, but for some enzymes in some situations it might be 60, just because there might be a big variation in what's normal for that population. But the other thing, as I said, there's more than one. You can use a smaller number to detect short-term problems, and a much larger number to detect long-term stability issues. So you might use more than one block size to detect different sorts of problems. But it depends on your population and the measure and. So that's it. You can't say a standard number.
Okay. Well, we really appreciate your time and your knowledge. This is incredible. Thank you very much for your cooperation and for giving us this opportunity to listen to your expertise. And we look forward. We will be sending you the samples. Sorry. The questions, yes, questions, not the samples, the questions. No. And if you are very kind, you can forward that to us. Thank you.
And it was a great pleasure and a privilege to talk to you. So thank you very much for listening. I hope it's been useful. Thank you. It was lovely. Thank you very much.
Thank you. Okay.
All the best. Have a good conference. Bye-bye.
Bye-bye. Bye-bye. Okay, for the audience, if you didn't listen to this before, perdón, la audiencia, si no escuchó información que dimos antes, van a recibir su certificado por correo electrónico. Y bueno, las preguntas se le van a enviar al doctor Tony para que amablemente nos las responda. Y de parte mía y de los organizadores, pues muchísimas gracias por su atención. Creo que ha sido una excelente oportunidad de escucharlo a él y pues no sé si de parte de alguno de los organizadores quieran hacer comentarios, pero a mí se me hizo excelente la participación del doctor Tony y sobre todo la participación de la audiencia, de todos ustedes, en estar en estas conferencias. Muchísimas gracias. Hasta luego.